Now that we know how to start an MCMC run, we turn to the other main problem of MCMC samples, which is their dependence. In an ideal world, we'd like an algorithm to give independent and identically distributed samples from our target distribution. When we have complicated distributions, our normal methods for sampling IID values do not work, and so we have to turn to MCMC, and we have to put up with some level of dependence between the samples. Let's generate some MCMC dependent samples and make some plots to illustrate the problem. We'll return to the doubly truncated problem from earlier and generate 1000 samples. To get some plots and statistics which are specifically designed for MCMC, we import the RVs package. It gives us a simple way to plot the autocorrelation of the MCMC samples that we just generated. The x-axis of this plot is an integer offset, and the y-axis is the estimated correlation between our MCMC samples, which are separated by this offset. So, for example, if we look at x equals 1, then the y value will show us the correlation between consecutive samples in the MCMC chain. At x equals 2, it will show the correlation between sample xn and xn plus 2, and so on. At a higher level, we can look at this plot to see if there's still some significant dependence after a lag of, say, 10, and then conclude that our sample is not a very high quality one. Looking at the trace plot, we can easily see that the numbers are highly correlated. It kind of looks like a stock price chart, when we'd rather it look like random noise. Plotting the histogram of our sample against the target PDF, we come to the conclusion that our sample is pretty rough. There are too many samples near 10, and there are no samples at all above around 28, so it failed to explore the right tail of the distribution. This is quite heuristic. One simple numerical test is to look at the fraction of proposals which were accepted in the MCMC run. The diff function gives us the difference between consecutive elements of the exit array, and the fraction of these differences which are non-zero gives us the fraction of proposals which were accepted. The result is 84%. What do you think this number should be? Pause for a second and try to guess what the acceptance rate should be in an ideal world. It turns out to be about 23.4%. At first, I'd say this is very counterintuitive. The problem with this sample is that the size of the jumps which we proposed were too small, and so the Metropolis accepted nearly all of the proposals, but we didn't explore the whole support of the target distribution fast enough. Another numerical tool we have is the effective sample size. I like to think of this as like an exchange rate. If I know the right exchange rate, I know that if you offered me 100 euros or 150 Australian dollars right now, I know which one I would prefer. In a similar way, if you offered me 100 IID samples from my target distribution or 1000 dependent MCMC samples from the target, I'd need to know the effective sample size of those 1,000 dependent samples to be able to see which one is better. In this case, the 1,000 dependent samples we generated is only about as valuable as having 16 independent samples from the target distribution. This is very small. So the high dependence of our samples is caused by having very small jumps, accepting too many proposals, and then ending up with a small effective sample size. To combat this, let's just make the jumps bigger. Here's the same code as above, but the jumps are normally distributed with mean 0 and standard deviation of 20. We now see that the acceptance rate of proposals is about 27%, which is close to that magical 23.4%, which the elders of MCMC tell us is a good target. Looking at the effective sample size, we are now at 90. This is still much smaller than 1,000, but we improved a lot from the 16 we had before. Our autocorrelation plot looks a lot better. The correlation gets quite small after a lag of 10 or so. So while this isn't perfect, it's an indication that the sampling is good enough. The trace plot looks more like noise, though due to the lower acceptance rate, we can now see those regions where the chain stays at the same value for a few iterations before accepting a proposal. Finally, comparing the histogram of the samples to our target PDF, we see a better agreement of the two than before. We only have 1,000 samples and only 90 effective samples, so we can't expect the two to perfectly align. We need to run the sampler for much longer to get that. When we increased the jump size, we could easily have gone too far. Let's choose 100 instead of 20 for the jump size standard deviation. Now we accept 7% of proposals. The effective sample size is less than half of what it was in the previous sampler, though it's still better than in our first sample. The autocorrelation has also increased. Even though each proposal is very far away from the original position, the fact that the chain almost always rejects proposals and stays in the same position increases the autocorrelation values. The trace plot now has long, flat sections. And the histogram is a mess. As mentioned earlier, this target density isn't actually so difficult, and we can simulate IID samples using the inverse transform method. If we ask for the effective sample size of these independent samples, we get a much bigger number, 909. Note that the real effective sample size is exactly 1000, but the RV's ESS function just gives us a kind of rough estimate of this number. In any case, 900 is much bigger than the best MCMC value we got which was about 80. The autocorrelation plot is basically 0. Again, the true correlation between these perfect samples is 0, and the plot just shows an estimate of these true values, hence the bit of noise that's shown here. The trace plot looks like noise. And the histogram agrees quite well with the target PDF. If you look online, you might come across some bad advice relating to this topic. What I'm referring to is the fact that you can make your autocorrelation plots look better by subsampling. Here, let's sample 10 to the power of 5 highly dependent MCMC samples. If we pull out every 100th sample and put it in a vector named x sub, we see that we are left with just 1,000 samples. Comparing the autocorrelation plots between the x vector and the x sub vector, we see that the x subplot is far closer to the ideal plot above, which indicates that the x subsamples are nearly independent. And if we look at the effective sample size of x as a fraction of its length r, we see that it is a very small number, indicating that each individual sample is almost worthless. Doing the same for the x subvector, we get this ratio is about 40%, which is much better. In other words, the x subvector contains about 40% of the information that would be contained by an IID sample of the same length. But at the end of the day, this relative effective sample size is not important. What matters is the overall effective sample size. Comparing these values, we see that the big X vector of highly dependent samples still has a higher effective sample size than the small X subvector of nearly independent variables. The difference is not huge, and so it's somewhat surprising to see that we can throw away 90% of our MCMC sample and only suffer a small loss in the effective sample size. But it is still a loss. The only reason it'd be worthwhile to do this is if you were generating a gigantic number of samples and they couldn't all fit in memory at the same time in your computer. Then subsampling would allow you to save a lot of space while only taking a potentially small loss of information. In conclusion, if you plot the autocorrelation plot and it indicates a highly dependent sample, other than changing the way that you sample to reduce the correlation, the only thing that you can really do is just increase your sample size and generate a lot more of these very poor samples.